school here on campus, these two buildings, they have the science fair, which means they have science exhibits outside normally, but it has been raining, so they probably brought them all inside again.
No, they were inside 1 hour ago. They were outside 1 hour ago.
Yes, and now they might even run into their lunch break soon. But if the weather is good after lunch or something, I encourage you all to go there and look through these exhibits. My son is also there, making one of the exhibits. He's in the grade 9 already, so it's the last time for him. Today we have on the schedule practical issues about the 3D and 4D bar for numerical weather model prediction. And it's a pleasure to welcome Gustafsson, who is at the University of Linköping and has been graduating originally in mathematics at the Uppsala University and has been associated with data assimilation for quite a long time. He has been working and exposed to that field since 1967 by Leonard Bengtsson, who introduced him to that field and has been developing that field from the first hour onwards. It's great, therefore, to hear from you the practical issues associated with that data assimilation. He has been in a variety of different fields, and because he has been involved in all these practical issues, he was not forced to do a PhD originally in these early days, and I know a number of other people who did that. But of course, being an active research scientist, it is a natural and in fact not such a difficult thing in the end to actually do a PhD anytime that becomes an issue. And so he did his PhD sometime in the mid-90s, and has been associated with Stockholm University also in the meantime, where he has been teaching with courses and medical stuff. So it's a pleasure to hear from you about the practical aspects of the submission.
Yes, I included in the practical aspects a little bit more details about what my wife talked about last week about the hybrid variation and ensemble data assimilation, how we really implemented it. And maybe my talk will be less practical than intended. I should say also that I have done this in something what is called high resolution limited area model community. It's Nordic countries, Netherlands, Ireland, Spain, who work together on the numerical weather prediction system, and there are many colleagues being adding things to this. So we work with regional model data assimilation for models with a grid resolution at present from 5 kilometers, say, to 20 kilometers, and with areas including Europe, part of North America, Atlantic, and mainly then on, you can say, somewhere in between mesoscale and synoptic scale, what we said. But we are now moving towards what can be called cloud permitting or cloud resolving models with a resolution of 1 kilometer. And there I would say that it's very open how we should do data assimilation. We have not come very far there. So this will be mainly about synoptic scale data assimilation. And the VO40 bar, I guess you are all aware of it, so I should not say too much. We have a background state, we can run a forecast from that. And then we try to adjust, we run a forecast from that, and we try to adjust the model solution to the observations. And in order to do so, in order to have a minimization problem that we can tackle, we normally have a tunnel linear model to run forward for a perturbation. And then we have a joint of that tunnel linear model to carry the gradient of the arrow backwards in time. Then we then minimize for the initial state at the beginning of the window. And in addition to 40 bar, it's also a 3D bar because you have a background constraint with a simplified background arrow covariance here. And that background arrow covariance is static. That's why we are interested in using ensembles to make it more, let's say, flow dependent. The time windows normally can be 6 hours, but that of course depends on the processes. This is fitted for, let's say, synoptic to mesoscale scales. If we want to run on a cloud permitting or cloud resolving scale, probably we should shrink this window to a few hours or so. And the equations are that we have seen them, I think, in yesterday, are the incremental variational data assimilation equations, where we have an increment that can have a reduced resolution in order for us to make it feasible we have reduced resolution. So it can be 2, 3, 6 times the normal model resolution. And also in the observation and operator we include the time and linear model, and that normally is also a simplified model. The dynamics is, I think, normally treated completely as it is, but the physical processes like condensation, clouds and so on, we have to simplify. They are too non-linear and maybe even too expensive to run in a variational data assimilation, so they are heavily simplified. Because when we designed this, it's in fact 15 years ago, we designed this variational data assimilation, and it took us 5 years to do the 3D bar to make that operational, and another 5 years to get the 4D bar operational. So it's quite a heavy, I would say, development investment to do such a variational data assimilation with 4D bar. When we designed it, we decided to use a spectral version of our model. We had both a finite difference version of it and we had the spectral version. And the main motivations for the spectral, maybe because I knew it better, is one reason. But to do the Tanner linear adjoint with the spectral model is somewhat simpler, because you don't need to consider all the finite difference schemes. You have put all spatial dependencies into the Fourier transforms, and they are simply self-adjoint. The adjoint of the Fourier transform is the inverse of the Fourier transform, so that simplifies things. That's possibly in the atmosphere, but I guess not in the oceans. No. But later on, it complicates things, because in order to have it feasible on the computers, we need to introduce something what is called semi-Lagrangian time integration, and then we are back to the spatial dependencies. I will say a little bit more about semi-Lagrangian scheme problems. And also we use the spectral technique in the background error constraint. If you assume horizontal homogeneity with respect to correlations, you can go to spectral space and you will have independent variables. That is also a nice thing with the spectral approach. But in order to use the spectral approach on a regional domain, we do a trick, we do an extension to make it double possibility of double periodicity. And when you work with it with data assimilation, you represent also, in fact, the correlations with this extension zone. So this means if you are less careful, you can have influence from here to here, if this is too small, these extensions. So it needs to be wide enough to let the correlations go to 0 or so. That's the main trick. So that's it. And just some comments on the coding. There exists, as Olivier told the other day, automatic preprocessors that can do the adjoints for you and time and linear codes. We did it manually some 10 years ago for the Valerian and later on for the semi-Lagrangian scheme. We compared. They gave exactly the same answers, and the manual coded one was of the order of 2 times faster. So I think it is at least with the ones we have tried, it is an advantage to do it manually. You can see something that maybe is not so easy for the preprocessor to do. The main problem we had has in fact been with the semi-Lagrangian scheme. I don't know in your world if semi-Lagrangian time integration is common, but the idea is that for every time step you calculate the backwards trajectory, and it always arrives in a grid point. That's the way. And then you do at the departure point, you do an interpolation by some high order interpolation. semi-Lagrangian scheme. And the advantage is that you can use very long time steps for it. It's no restriction of time step due to advection. That's the main advantage. But you need to be a bit careful how you, for example, treat nonlinear terms along that trajectory. You need to have extrapolations of them in time that are stable. But there are possible such schemes. So that's what we introduced to make it, let's say, computationally economic. But we, rather late after we've done it, we detected the problems with it. Because when you make a tangent linear version of a semi-Lagrangian scheme, you need to stay within the same interpolation volume for the departure points. Because you want the tangent linear model must be continuously differentiated. That's a requirement. And that means that you must stay within this interpolation volume for the tangent linear scheme. And in case you have and then you will have two terms. You will have let's say, advection of the perturbation field by the normal, along the normal trajectory, but you will also have advection of the basic that you linearize around with the perturbation. And if the wind increment, due to some reason, you have a poor wind, is very large, you can go outside this interpolation volume, and you can have a drastic serious effect by this cubic interpolation, for example, if it's too large.
So in order to arrive at a mesh point with your Lagrangian scheme,
Yes.
you need to iterate, or?
Yes, we iterate. We have 3 iterations to find the wind at the midpoint. Yes.
And then you...
And then that is done by extrapolation of the wind, and then you find the midpoint of the trajectory in the first iterative scheme.
But the values that are transporting along, you take them entirely from the past time or also from the middle?
Now you take them from here.
Yes.
Until here. Yes. Normally the things.
And you say from here until
Except that.
So when do you evaluate the right hand side? Only of the...
Yeah, so then we in fact what complicates it further is that it is semi-implicit also. Yes, so you solve the semi-implicit equations along the trajectory.
So it's actually, okay, so it's actually then satisfied in the middle of the point.
Yes.
Exactly.
Yes.
Is it second order in time then? Or?
Yes, yes. So you don't use that in your world, or?
We use, I use third order time steps, but they are Eulerian.
Eulerian, yeah. Now normally you can take the time step maybe that's 3-4 times larger with the semi-Lagrangian. That's the advantage.
Yes.
Of course, sometimes you can cheat if you, for example, make trajectories that passes several mountains or something like that. Mountain orography, so it's you should not take too long because it's stable, I would say, for any time step.
You also have sound waves, don't you? Or they are
not in this version of the model. We only have delta waves, and these we treat by a semi-implicit time integration.
By the one you mentioned.
Yes.
And you're solving the inelastic equations then, or how do you?
No, it's the hydrostatic for the moment. Hydrostatic equations.
Yes, I see.
Yeah.
Right.
Yes, but we have similar techniques also for the more complete equations. We have non-hydrostatic version of the model. So, yes. And this, in fact, caused us a problem once. This problem with a large wind increment. People were running a data impact study of observations. They found a good impact of some observations, but they could not tell me which observations were good. And I went into looking into this problem and traced errors and so backwards, and I found that it was an instability due to this that gave in a bad impact in the reference case, but with more satellite data it did not occur. So I would say that I will show you many scores of forecast verifications. It's very dangerous to only look at that. You must really look into the processes also if you want to have prove anything.
Because it's not really due to the non-linearity, but it's just that you somehow, you're not like if you have an explicit scheme, you're limited always inside the box. So that's the reason. It's not
Yes. You can say that the semi-Lagrangian scheme when it's tangent linear version of the Kamsen-Weyl area characteristics. You can say, yeah, that's the problem. And we did not think of that first. We thought that tangent linear of a semi-Lagrangian would stay semi-Lagrangian, but that's not the case. Yeah. So then that's the adjoint model. Other problem is, of course, background error constraint and the huge background error covariance. If we have 10 to the 8 model variables that we can have. So I think Jenny showed that already yesterday. We use this transform method. We do a go to spectral space. We balance the operators and keep unbalanced variables. We normalize the horizontal spectral densities. We project on vertical eigen functions of a vertical covariance matrix, and we normalize with this. And we can end up with something that we can assume have an identity covariance matrix. That's the way we do it. Of course, this can be questioned. Hi. This can be questioned because there you assume you assume homogeneity with respect to correlations. You can come past that by using wavelets, which permits anisotropies, and you can do like we do a hybrid scheme in order to have more natural flow dependent structure into the assimilation. So the balance is a standard one applied by many things. We start with the vorticity, and then we make for each spectral component, we make let's say a balancing operator in the vertical, so that we connect the divergence to the vorticity, and we keep an unbalanced divergence. And then we do the same with the temperature and surface pressure, and also with the moisture. So this was introduced for us by Louis Berg. The main change we have made to that we have now taken the spatial variations of Coriolis parameter into account. I'll just show you a few such how do you derive these structures that you need for the background error constraint. Long time ago, something that people don't like at ENSO, the NMC method was developed, where you try to take differences between forecast values at the same time as a proxy for forecast errors, in order to have a full model space forecast error process to calculate the statistics from. Another way that we are using mainly now is to do ensemble assimilations. In some way you perturb in your forecast modeling observations, you run the whole ensemble of forecast, and then you can calculate the statistics from the differences between the ensemble members.
So as you perturb the observations?
Perturb observations, the normal thing to do is perturb observations according to their errors. Mm-hmm. Yeah. Mm-hmm. But then you let the model develop by the stabilities and so on. The model, you let them develop the perturbations so that they become more realistic and similar to forecast errors. Of course, that is also a bit doubtful. You perturb over areas where you have observations, but over the Atlantic where you don't have any observation, you don't perturb. So of course that is questionable also. So I'll show you some few statistics, what you can arrive at. You will have horizontal spectral densities, for example, at different levels. And you can, this is just the function, the spectral density as a function of wave numbers. And you can see in these spectral densities, for example, that at the high resolution end of the spectrum you can have noise. Normally we try to take that away, we don't use that. And you can see the vertical dependencies of the spectral density of a larger scale at the upper levels. You also see a funny curve there. If you can guess what that is. Now, such of those practical things that arrive at the weather service, they store things into not enough accuracy. So moisture in the stratosphere was not stored, it was all zero. And in order to avoid ill-conditioned vertical covariance matrix has introduced the noise in those levels. And then we had a flat spectrum. Quite stupid. So then we can look at what can these balance operators do. And this just shows the fraction of variance of temperature explained by the vorticity and by the divergence, unbalanced divergence. What you see here is mainly the degree of geostrophy as a function of levels here. Maybe 50–60% in the mid-troposphere, and as a function of horizontal scale. You have a decrease in the geostrophy with wavelength. That's what you see, and you can utilize this in your assimilation. And then you can see also specific humidity, how that is explained. And you can say that two things you can see is that there is certain degree of a relation between vorticity and moisture, mainly frictional inflow in, let's say, developing low-pressure systems. And you can see a relation to temperature, mainly, I would say, relation to condensation at mid-tropospheric levels. And when you use these structure functions, you can get, for example, this is surface pressure increment and lowest model level wind increment. You can see that you can get the frictional inflow. This is with the so-called NMC method, and this is with statistics derived from ensemble assimilations. And you mainly see that to the NMC method you get larger scales than in the ensemble assimilations. Probably, I would say, I'm not so certain, mainly due to that you take different, bit longer forecast. It's likely that longer forecast would have larger scale forecast errors.
Are these inhomogeneous? I mean, when you're...
No, they are homogeneous, yes.
Okay, but you just said that you have no observations, so to perturb already explained it, right?
No, but these are homogeneous. They are derived from the total. This is just a simulated observation in the middle of the Atlantic to illustrate the structure functions. Yes. If that's what was your question?
The question was if you have no observations to perturb in the ensemble method,
No. Okay.
how do you do it? And you just
Now we derive the structure functions from the whole domain and use them by homogeneity assumption in this
okay,
case.
so you do use a homogeneity.
Yes. So another practical issue in data assimilation that maybe is not talked much about in theoretical courses is quality control of observations. There are a number of observations. Some of them can be quite wrong. So we have different, I would say, sets of quality control algorithms. We have, before the assimilation, we throw out as many of the crude errors as we can. And within the data assimilation, we have what is called variational quality control. In order to derive this, you have to take a step backwards from the cost function for the formulation or variational data assimilation and go back to the maximum likelihood formulation and to insert what are the probability distribution of errors. And you can have, for example, errors of scattering headwinds. That could be 180 degrees ambiguity, and you can formulate that within a variational quality control. Or normally we assume that, for example, surface pressure measurements from the ship can be identical probability density function, constant, over a certain range, and you can insert that. So that helps to, in case of such a probability distribution, the cost function becomes flat for large difference between the observations and the model. And when they come out there, we can consider them as back or rejected. So that helps when you insert, and we insert this in the minimization over a certain range of iterations. Here you can see that we insert this part of the probability distribution, and you will have a reduction in the cost function. And then we iterate for a while, and then after after a certain number of iterations, throw all that are out of this flat range of the cost function. And then the cost function reduces further. This is quite important for numerical method prediction to have a good quality control system.
So Niels, it's an interesting model. It's probably not the one that a statistician would reach for. I think they would typically work with a class of distributions for which you could control the fatness of the tail, and then you would dial down the fatness of the tail as you iterated the scheme. So I'm thinking, for example, about iterating through the student T distributions to arrive at a Gaussian at the far end. You know, so, or starting with the Laplace distribution, which has very fat tails, to get your algorithm going, and then after a while switching to a student and then switching to a Gaussian. I think it's. I think that this is an unusual scheme that perhaps hasn't been hatched by a statistician, but
Obviously been hatched by a practitioner.
I'm sure it works, except for the missing sigma squared. I should point out in that formula, which is there should be a sigma squared under the zi squared.
Just one question also: is those errors are mainly systematic errors?
Now, they are random errors due to sending wrong positions of a report or something like that, or even very crude things.
Yeah.
Somebody is drunk and still reports. Yes.
But I think we spoke, and I guess you will get back to that point, that in some cases, those very atypical observations, it's exactly what you want to do to predict a hurricane or a big storm.
Yeah, that's the problem.
So that's the typical problem, excluding the rare events, because they are
you
what
can
you
say that I want maybe one should call some of the assimilation systems are a bit stiff.
Yeah.
It takes a time before they react to something strong events, because they start to react to observation in those events. I have an example of such reactions for the storm of the France 1999.
Long time.
So, of course, I will not tell much more about observations, but of course, important where we put a lot of efforts is remote sensing observations in our work. For example, the variation seen by satellite. And we normally, I think the experience is that before using directly the measurements in the assimilation, we had problems to see the good impact of that. But once we started to assimilate what the satellite sees directly, we have a better impact. So normally now, most groups, they assimilate directly the radiances in the assimilation. And this is such a diagram I will show you several of, where we measure the proof of the pudding lies in the eating. Somebody said that the personalized a long time ago. We measure the impact by looking at the scores for the forecast. And these are the scores for the 40 bar round without satellite answer measurements, and this is with. So maybe you can see an increasing predictability over 3-4 hours over such a limited area domain from the satellites. Normally, everything you do, you will see maybe a few hours improvement. But you have to do many things in order to have strong improvements when you do work with data assimilation.
What are the lower ones?
There are two versions of the satellites. One where I used a channel that was sensitive to the surface and not. But it seems that it does not destroy too much. The problem is that the satellite radiances are very sensitive. Some channels are sensitive to what happens at the surface also. So you have to have a very good lower boundary condition to utilize them efficiently. So that's why we mainly use those that are less sensitive to the surface conditions. Ideally, you should assimilate the surface conditions also, but we are not there yet. So I will not say more about observations. I will say a little bit about the advantages of 40 bar over 3D bar. And the main advantage, as I see it, is that you get flow-dependent influence of observations. Due to that, you can. I did not bring the proofs here, but you can consider 40 bar to be the same equivalent to an extended Kalman filter over the time data assimilation window. But you assume a static covariance matrix at the start. But in the window, you will get flow-dependent influence of observations. So ideally, one should also have, of course, at the start of the window, something flow-dependent. But for the moment, when we run for the in this way, it's flow-dependent only inside the window. And this is something I did a long time ago. I tried to do such a single observation study. What will be the impact if I try to have a 5 hectopascal pressure decrease in the middle of the storm, 5 hours into the assimilation window? And what will be the increment if I do it here in a less dynamically unstable area? And the result was this. With the 40 var and an observation there in the middle of the storm, 5 hours into the assimilation window, I get this increment at 5 plus 5 hours. You can see that this same scale as the storm. So that is determined through the use of the linear model, linearized over this storm development. So that's the advantage. While with free var, you get these stiff static structures. And in this case, if you run it with a nonlinear model, you have a very similar increment if you start the increment. And at the start of the window, it was interesting. I didn't need to change the surface pressure very much. I need to change the thermal wind, the vertical thermal wind in the vertical, the conditions for the instability. So this was what was the main increment at the start of the assimilation window, an increase in westerly wind at some upper levels, and even a sort of a tilting system. So you need to change the baroclinicity in order to have a stronger storm development. While if you worked out in these unstable areas, you made an increment. It's slightly deformed due to advection. That was mainly an advection of this pattern over the time window. So it's really dependent on the flow, the structures.
When you say you need to change the baroclinicity, what exactly do you do for that?
I mean that you increase vertical wind shear. Vertical wind shear is a sort of related to baroclinic instability.
Yeah.
And if you change that, you will get a stronger storm development.
I see.
Yeah. While here it's less unstable conditions for such a development.
Why do you use 5 hours rather than 6?
I don't know. For some reason, it was easier to do at 5 hours. Yeah, another important issue in numerical weather prediction is, of course, fast oscillations. If you take a shallow water model, it will have slow development modes and it will have fast gravity modes that oscillate and create, after a while, the geostrophic balance. But if you insert observations at the start that are not properly balanced, you may come here. And that was Rickardsson did in his trial to integrate numerical weather prediction model in the 1920s. He integrated a fast mode, you can say, and get what is considered as an absurd increment or tendency. So how do we handle that? And I stole this figure from Jean-François Arcelin. It's a nice figure of the circle that we have gone through with the initialization and numerical weather prediction. I didn't put you there. You had something also some time ago.
Oh, that was a long time ago.
Yes. So Hinkelmann already in the 1940s had the idea that you should have a sequence of time tendency or divergence equals here. Then you could have a proper start of numerical weather prediction. And we started with that, and that I helped Stockholm University a long time ago to solve the nonlinear balance equation. That was the first trials. It did not work very well. Later on, people worked with a stable, to say, forward vector and damping time integration schemes. Then we came up with a normal mode decomposition.
It was Nika and Hovener,
Yeah.
the forward vector. And then actually what Olivier Talagrand did for his PhD thesis, Olivier Talagrand,
Aha, yeah.
did that with the shallow-water equations,
Yeah.
and it's only afterwards that he realized that, you know, since shallow water is hyperbolic, the forward backward was essentially variation.
Yes. Yeah. And then we came up with
The, you know, the adjoint is the same as the
Yeah.
operator itself.
Yeah. So next step was the composition into fast modes and slow modes, linear novel mode initialization, where we put the gravity modes to 0. That did not help very much. It was still oscillating. Then, as I considered the bright guy, then at Machenover came up the idea of non-linear mode initialization. He iterated in the equations in such a way that he forced the time tendency of gravity modes to become 0. And that helped, and that stayed for a long time as the initialization scheme. And then there were even such a time integration scheme. I think Roger Daly worked with that for a while. Daily time stepping that used this idea in the time stepping itself. And then Peter Lynch from Ireland came up with the idea, a simple idea. Run the nonlinear model, apply a digital filter to the output, and use the filter state. And wonder, it turned out to be fine, the time integration with such a filter state. And then the last part that comes very close, I would say, to Hinkelmann's idea is the weak digital filter constraint in the 4D-hard procedure. You try to force the fast tendencies to be 0 over the assimilation window. And then we are back at Hinkelmann's idea. That's what we have introduced. So the idea is that...
Let me just say, since you did mention, you know, in the work that I did, there was some theoretical work that I did that I don't want to go into now, but in the work that I did with the NASA group,
Yeah.
actually, you know, we just had a time scheme that was doing the Irish thing all by itself.
I see.
So the reason that in that 1979 paper on satellite data assimilation we didn't use any of this is simply because the damn thing died out anyhow.
Yeah. Okay.
So, yeah, so there wasn't much of a fuss to make about it.
Well, okay, I should move in the right direction here. So what you do, you put in a constraint where you try to come close with an increment to a digital infinite increment, for example, at the mid time of the window. You can say you try to find in the minimization something that is close to the slow manifold, to the slow evolution. And then at the same time you try to stick to the observations. Don't go away too far from the observation. That's the idea. And it works reasonably well, it seems. But again, that's the question of an unknown coefficient in a weak constraint. How should you assign that coefficient? We did it a bit ad hoc, I would say. We ran trials with different coefficients, and we looked at the cost function fit to observations. It's here. This is with a larger coefficient in front of this constraint, you go away from observations. And in the larger coefficients, you get less and less noise measured by the tangent linear delay, or by the digital filter deviation in the tangent linear integration. So you have to select something that kills the noise and still stick to observation reasonably close. Does that help then when you go to the nonlinear model? Yes, it seems so. It seems that if you reduce the noise in the tangent linear integration, even at the coarser resolution in the tangent linear model, you reduce the noise at the start of the nonlinear model with a high resolution.
Yes, I just need to ask a really naive question here.
Yeah?
So gravity waves are a property of the atmospheric system, and they are present in the observations.
Yes.
So one would imagine that they ought to be present in the forecast as well.
Yes.
Okay.
They are, but I would say, I look upon it like this. that gravity waves, they adjust by eustrophic adjustment.
Mm-hmm.
In the atmosphere, it's an ever-ongoing process that keeps them on a low amplitude. But when you insert one deviating observations, you destroy too much. It gets too large amplitude of the gravity waves.
So is it the case then, if you were able to run these models at higher resolution, you would not need to worry so much about the presence of gravity waves?
You will have to worry more when you go to high resolution, and many gravity waves are not that fast. When you go, for example, to, I would say, mesoscale phenomena and condensation process, they are less deep, the gravity modes.
Mm-hmm.
Maybe you correct me if I'm wrong.
I have to say something afterwards, but what you're saying is correct.
Yes.
You see, this whole thing about, I mean, you have to realize that this whole issue of the slow manifold, you know, why is most of the energy in the Rossby waves and not in the gravity waves, is a problem complicated enough for Ed Lorenz to have written 3 papers in which he said, you know, there is a slow manifold, there isn't, and I don't know, essentially. So there is something like a fuzzy, you know, finite amplitude manifold, but you don't have enough observations to deal with that correctly. You know, so you might just as well get rid of them because, as Niels was saying, they sort of get in the way. The tendencies that they put in are large.
Mm-hmm.
And the way that the model deals with that is not the way that the atmosphere deals with that.
Right, and that's not just a problem of model resolution. Is that some aspect of the physics that's not correctly implemented?
I think, look, the thing is that it's quite clear that there are places on small scales where the Rossby wave, where the inertial gravity waves do interact with the flow in substantial ways. I mean, you know, if you have a lot of convection, you generate a lot of, you're alluding to that, a lot of inertial gravity waves, and they might affect the large-scale slow flow. But and if you have, when you have fronts, you have, you know, and steep topography generates lee waves and so on. So they are there, but there's just no way that they that you have enough observations to deal with them correctly. So it's better to get them out of the way.
Are they really very important for the weather? I mean, if you want to make a short-term weather forecast, you need to predict very well gravity waves. And it's also the reason, because if it is not unbalanced, you have lots of noise, but in the end, you can get a more quite similar forecast. Yes,
you can say if it were only for forecast purposes, you probably could let the model do the eustrophic adjustment. But the problem is that we very quickly want to insert new observations, and then we don't want to have these fast oscillating waves. Is the main thing, as we see it.
You know, it's what you project your observation on. In some sense, you don't have a good handle on. You know, I mean, how much of it goes onto the Rossby waves and how much of it goes onto the inertial gravity waves. This is something that is far in the future, if at all. You know.
Okay. So then another practical issue is, of course, that we want to be able to solve the 40R problem on the computers we have. So we have implemented what we call the multi-incremental minimization. We run first at the coarse resolution and then a finer resolution later on, in order to become part of the solution at the coarse resolution. So the formalism is there, but it's mainly that the main issue is that you do re-linearizations between the different iterations, of the loop iterations. Because you need to refine the tangent linear approximation. But you should be a bit careful with this. We also have noticed that if you iterate too much at the coarse resolution, you may project on too long waves. And then when you start with a second outer loop at higher resolution, it turns out that you go back. You take away some of the longer waves inserted in the first outer loop, and then you insert shorter waves that I wasn't described in the observation. You get some aliasing effects if you do too many. So you need to be careful with the design of such a multi-incremental minimization. But it is important. I show now such forecast impact diagram. The green curve, these are surface pressure verification scores. The green curve is a run with 44 kilometer resolution in increments, 100 iterations. Now that is 66 kilometer, 100 iterations is the red curve. You see the very little difference with the two increment resolutions. But if you apply 50 iterations with 66 first and then with 44, you get an improved forecast even. You can measure it even there. So what it says is mainly that you need the relinearizations. So then, just before I go and talk about our implementation of the hybrid, I will just show one. We have done parallel runs compared 3D-VAR and 4D-VAR for, I would say, a year on parallel runs. And the same, the figure come out for every such month. You have a clear improvement by 4D-VAR over 3D-VAR. This is a run we made. Again, it's surface pressure over the whole domain. And the green curve is verification scores for 3D-VAR, and this is for 4D-VAR. And you see a particular thing here at the start of the window corresponding to the analysis time. Even the 3D-VAR deviates with the analysis from the observations. That is in fact the quality control problem with 3D-VAR. With 4D-VAR you get fewer reactions of the observations, and because of better structures, and you get better first guess and fewer reactions. So I'll just show a few maps, how it can look like, what improvements did we do. It's not very clear here, but this is a 30-hour forecast. Yes, I would say that 99, I think there were at least 3 storms over Europe, devastating storms, that everybody has been running with. And some of them are very sensitive to almost anything in the initial conditions. There was one over Denmark, 3rd of December. And this is the forecast with 30-hour forecast with 4D-VAR, and this is with 3D-VAR. And these are the analysis with 3D-VAR and with 4D-VAR. And you can see an improved position and intensity with 4D-VAR. And similarly, for this second French Christmas storm, this is now a very short-range forecast, a 6-hour forecast based on 4D-VAR. Then you catch this storm development in the sea areas, so that when it enters land, it's already developed, and you have no difficulty to come up with this analysis when you insert observations. But with the 3D-VAR, it was very crude, and it started to react all observations almost over France, what you saw in this verification curve.
You know that storm actually blew the roof off Olivier Talleyrand's office.
That was a strong storm.
At the time I was a visitor, and I had the office next to his, and I was lucky, the roof over mine held. But when he came back from the Christmas vacation, there was water on the floor, and if you know Olivier, there were lots of papers on the floor.
But it's good for Olivier, then the 4D-VAR can help. So what does 4D-VAR make better job than 3D-VAR in storm cases? I would say improved implicit structure functions, better quality control. What I have not said is that with 4D-VAR we use slightly more observations, because we have, in 3D-VAR we only have an increment at one time, and we only take the 3D-VAR data selection, mainly the closest observations in time. But 4D-VAR we have 4. For example, we can have 6 observation windows within the assimilation window, and we can utilize the time tendency of the observations also. We have slightly more observations. But in general, I would say I've done many such parallel runs. It's quite difficult to find one specific reason for the improvement. It's gradual improvement of the assimilation of the whole several cycles that gives the improvement.
Niels, do you think that that the adoption of an approximation technique like FGAT, Søren mentioned the other day, do you think that would get 3D-VAR quite a long way to performance of 4D-VAR?
So I didn't get
FGAT. You basically, it's a 3D-VAR, but you run a reference, one reference run forward, and you take the anomalies of the measurements with
You
respect to the
get
reference
parts
run.
of it, but I would suggest
Who
that.
talked about this?
Well, Olivier has mentioned
Oh,
it in his
yeah.
recent review.
No, and I think it's used. It was used when we used FreeWire. We used FCAT, and I think in this round we use FreeWire. We use FCAT.
Okay.
Yeah, but you only get the, I would say, right, the non-linear, the background, right at the right time, but you don't get the time variation of the increment with FCAT. It's only halfway, I would say. So you can see that when I looked at, for this Danish storm, I looked at the assimilation increment. With FreeWire, you get this wide, smooth increments, but with 4D-bar, you get the flow-dependent input. So then I want to spend the rest of this talk on what you asked for, more details about our hybrid scheme. So the reasoning why we do this is that will assumptions on weak nonlinear, there is a 10 kilometer breakdown, will it be more nonlinear? Most likely yes. Can ensembles provide information? We think so. And we should not then, with this risk, we should not put all our efforts on 4D-bar. We should do something more. But should we really go to ensemble, common filter, and Arctic filters directly and leave all our investments? We should not. We should try to do a synthesis, is what we believe. I don't know if others agree, but that's how I see it. So then there are different approaches to use ensembles. For example, Mathieu France, they try to carefully go from what they have now, static covariance models, to introduce flow dependency into it by the help of wavelets, for example. That's one approach. We have selected another approach where we try to use directly the ensemble-based covariances and mix them in with the static covariances in a hybrid assimilation. And of course, ensembles can also be used to get better static background statistics. That's another thing. So then the first approach we have, I will not talk about our ensemble generation. We use what is called ensemble transform common filter rescaling of forecast perturbations to assimilate, to analyze these perturbations. I would say then we try to use these covariances from such an ensemble in the hybrid assimilation. I would say that this is the easy part. This is the real difficult part, to get proper, I would say, ensemble generation at the NISO scale. I think what we are doing so far is very crude. So that should really, there we are only at the beginning stage. I don't know if people agree with me. Do you, Michael?
Well,
Yeah.
as you know, I did a lot of hands-on assimilation in my early days. I've been off doing,
Yeah.
I'll be talking about more theoretical stuff tomorrow.
Okay.
So, but the idea of doing combinations of, variational and sequential is something that I totally agree with, and
Okay.
have suggested that in my 91 review paper.
Okay.
So I'm perfectly happy with that.
Okay. So how do we
I'm
do it?
also happy with the fact that ensemble common filters have a lot of problems.
So how do we do it? Well, I think there are several approaches to hybrids. And the one we are not using, maybe the easiest way to understand it, it's the paper of Hamel and Snyder. They suggested that you should just make a mixture of the ensemble-based B and a 3D-bar B and use that. And with some constraints on the weights there to preserve variance. And then normally one needs to do something if you have a small ensemble with localizing the ensemble-based covariances by something called a shoot product, or apply a local ensemble common filter. This is quite difficult to introduce into existing variational scheme based on minimization in model space. But if you do your minimization in observation space, this can be used directly. So then we come instead to the suggestion by Andrew Lawrence. He suggested a slightly different approach that we have adopted. So what you do, you consider your increment as one part coming from the Friedewald covariances, and another part that is based on the ensemble perturbations. So we try to do a linear combination of the ensemble perturbations as a contribution to the increment. And the weights here for the different ensemble members are space dependent. And this is just the same Schur product. And then you try to control these weights, the spectrum of these weights, for example, that you have. And that corresponds, in fact, to the length scale of the localization in the ensemble common filter.
Maybe you just want to say what the Schur product is, because I'm not sure that.
It's Schur product. It is just a P step, or element-wise multiplication of two matrices.
I think we would call that a Hadamard product, wouldn't we?
Hmm?
That would be the Hadamard product, wouldn't it?
Oh, maybe. We call it Schur product. So then we, to control the weights, we add another ensemble constraint on the weights. And we have a requirement to preserve variance. And the ensemble constraints. Then we introduce covariance for the weights. And in fact, we use the same preconditioning assumptions about these weights as we do for the other model variables. We treat them in spectral space with a certain length scale and with the variables. And it turns out that this was very simple to introduce into existing 3 and 4 university. A week of programming, I would say. And of course, then everything comes with the tuning and the testing, but the insertion itself was very simple. So there is a proof in the paper that they are equivalent. And as I said, the main advantage is that it's very easy to implement. And it's also implemented in Worf, and UK methods are also using this hybrid. And in the first version that we implemented, we only did, can say, horizontal localization. We assume that the weights for the members are functions of horizontal position only. And then we use the same simplifying assumption in the preconditioning as in the 3D bar minimization, and we assign a variance for the ensemble weights. That, in fact, can maybe be an interesting approach to give different variances to different members. If you, for example, can see from a satellite image that one member has a better phase error are difficult to treat in data assimilation, but if you see one member has a better phase, maybe you can give them a weight such that it gets more weight in the assimilation. That's just an idea. So this I already said. And we apply the same ensemble weighting to all model variables. And the model variables we introduce are vorticity, divergence, temperature, and specific humidity, and surface pressure. We try to avoid the wind components, because wind components, due to balances, have negative lobes and positive lobes. So you should not localize them. You will destroy completely the balance. So that's why we selected these for the localization. And for the minimization, we need to specify this weight. I will show you some sensitivity to these weights. The variance, we have so far only plugged in a very, very simple variance, 1 over number of members so far. So this is still a tuning parameters. And the horizontal correlation spectrum we need to put in. And when it comes to the horizontal correlation spectrum, that is the length scale of the localization, my view is that you need to include within the localization the phenomena that you are interested in. For example, if you have baroclinic development, you should probably have the order of 500 or 1,000 kilometer localization. If you shrink it too much, you will not get the phenomena you want.
Sorry, isn't Gasparian cone extended Kalman filtering rather than the root ensemble?
No, I only say that they usually apply for ensemble Kalman filter, but this paper is about how do you do localization,
Yeah,
and what
okay.
correlation models you use.
But it was really done in the context of extended Kalman filtering rather than ensemble.
Yeah, maybe. The curve there is not very clear, but what we do, we have a power law, and then we try to make the correlations go to zero at a certain distance, complete close to zero. You can say a compact correlation function, and then we do a Fourier transform on that in order to be able to apply it in our assimilation scheme.
So have you tried Wendland correlation functions, because they're a popular family of compact correlations?
I think we have a power law, and then we have a piecewise rational function that it's windowed by the. I should not. In fact, my work might be this work, but we windowed a power law.
You windowed it, so
Yeah.
you truncated it.
We multiplied it by something else, such that you get zero correlation at a certain distance.
Okay. And
What do you call the compact?
Wendland is the one that we tend to use, especially in spatial statistics. You know, in order to zero effectively small components in the covariance structure, we treat the Hadamard product with a Wendland, which has compact support.
But in fact, it turned out if we took the spectral density for the most large-scale variables we already used for the surface pressure, under the surface pressure, they worked well also. Very simple. And a bit ad hoc, of course. So I'm almost at the end. I will just show you. My wife already explained the general outcome of the hybrid, the promising results. I will only show you a few more slides that she did not show. So here we have the result of I would say, it's a short period for 5 days. And the green is where we mix with 50-50. The red is with pure 3D bar. And the other one is with 90% ensemble covariances. So it seems that when you put equal weights to it, seems to be a reasonable assumption. Of course, we have to do a lot more experiments and tuning here to find out what is best. In particular, we noticed that with only the ensemble covariance, we draw less for the observations. That might, and you see even with the hybrid, we draw for the observations, but the curve past the 3D bar curve after time of integration. It could be good or bad. It may be that in the 3D bar we have designed the variance such that we have a large variance everywhere. But that's not the case. We have a large variance we should have a large variance in sensitive areas where we have darkening developments. And with the ensemble we model this to have the variance where we need it. So it might not be completely bad that we draw less for observations, I would say. So I think that's the end. When concerning the hybrid, I think we need to do certain things. We need to look for need for vertical localization, but that becomes a bit complicated because we have observations that are vertically integration with complete atmosphere, so it's not so simple. And we should see also, this what I showed was mainly how it performs with 3D bar. We need to see that it also performs well with 4D bar. And we should improve, of course, the perturbation technique. This, I would say, is the first guess. We have done also an experiment where we perturb observations, what is called ensemble of data simulations at ECMWF. There they perturb observations. But this is a whole area where we need to improve. And then to go also for the higher resolution isoscale, we need to do something. And maybe these ideas of selection rather than, let's say, minimization by selection in particle filters could be explored also. So there are many practical things I've not talked about, but a few of them. So I'll stop there. If anybody is interested in how we do in other areas, please come and talk to me. Thank you.
Questions, please. 20.
So there's one key issue here is about what you really want out of your weather forecast. Do you actually want the best possible point prediction for, say, 24 hours ahead? Or do you want a well-calibrated assessment of uncertainty for 24 hours ahead?
And one,
well-calibrated assessment of uncertainty for 24 hours ahead. Now, in the climate community, it's still the case that they want the former rather than the latter. They're not ready to move to uncertainty yet. And they naturally plough all of their resources into one very high resolution model run. For the kind of resources that you're spending on your ensemble, right, how good a run could you do if you were only going to do one run? And how good do you think the point prediction of that one run would be compared to what's happening when you average over your ensemble of low resolution runs?
well, I cannot say that I have a clear view on that. I would guess that the 5-kilometer model ensemble could give as good information for the user as a single 1-kilometer model. But on the other hand, with the 5-kilometer model, you may not be able to resolve important processes for the weather, for the extreme weather, for example. So I cannot give a definite answer. I've always been on the line that I would like to have an ensemble instead. And as a user of forecast, I would like to have an ensemble. And I know people understand ensembles.
Do you think your ensemble is giving you a better point prediction, or do you think it's actually giving you a way into uncertainty? Uncertainty assessment.
Yeah, I think so, yes.
A better point prediction?
Yes. I don't know if I have other views on that than I try to express.
As a matter of philosophy of science, anything that doesn't give you an error bar is worthless.
I would agree, of course.
Yes.
So,
Yeah.
But you can get an error bar from a high resolution run if you look at the curvature of the cost function.
But you also have users who want deterministic forecast because they cannot treat uncertainties. They want to know whether it will rain or not. And
See, I hear that
because
said
they
a lot, but when you
decision
speak to
that
sophisticated
based on
users,
your
they're quite
focus.
good with uncertainties. When you speak to high-level policymakers, they actually are quite comfortable with uncertainty. I think it's almost a myth
yes,
that the
it
user
depends.
can't handle uncertainty.
I think if you have an activity that may cost you lots of money if you get a shower or something, so then you want to do something in advance, so you cannot just...
every economic decision has to deal with uncertainty. So I don't think that, you can tell whether there will be a shower or not. You can tell whether in 30% of situations there will be a shower.
But you originally disagreed with that, right?
I agree with that, yes.
You agree with that, yes.
But of course, there are buts there. If you cannot resolve the processes that cause this weather, then it's maybe not so meaningful with the coarse resolution ensemble. So I would like to have a high resolution ensemble, of course.
Yeah.
I was once in the room where they make forecast at the Met Office.
Yeah.
And actually the chief forecaster there, he was doing something, he was looking at different models at the same time. It was at the Met of France and ECWF and Met Office. And he knew about typical errors of each model because of the experience, and then he was looking at the ongoing data. So he was trying to correct what the models were giving by looking at different models and interpreting that.
Well, I still remember when I first was a visitor, at SMOE in the late spring and early summer of 1978. Sorry, not SM, at the NISU, sorry. I came over to SMOE and I saw, the people doing the forecasts with different models. What we would call today a heterogeneous ensemble.
Yeah.
And again, the experienced forecaster does, I'm actually amused to hear that, 30 years later, this is still the way it is done. I don't know, has there been some sort of a systematic discussion of localization here? Because I'm coming sort of late I would like to say a few words about this whole thing. I mean, you know, when we started with these two students, Steve Cohn and Dick Day, I was at the Cornell Institute at the time, and this was their PhD thesis, the applications of sequential estimation of common filtering. You know, based on my experience in the work with the NASA group, it was quite clear to us that with the computational resources of the time, you couldn't implement the full extended filter, and so that again in this 1979 paper with the NASA group actually looked at satellite data impacts in a realistic context at that time. You know, we had seen the importance of finite length correlations and so on. So the first idea of implementing a computationally viable extended common filter was to have it band limited.
Yeah.
Now the problem is that covariance matrices are supposed to have positive eigenvalues. And if you just cut it off, well, they won't. So that was the thing that Steve Cohn later already at NASA Goddard addressed with his student Gaspari. And so again, I was somewhat puzzled by the exchange between the two of you. You say that you're still cutting off the correlations.
Well, when we use
don't you notice some negative, the negative eigenvalues, these small negative eigenvalues?
Now we have not really examined. We have not seen any negative effects of it. Yeah, no, it's true.
Maybe at this much higher resolution, somehow things get.
But here, of course, we also have the static background with full weight, that is full rank covariance matrix, and we mix with this localized covariance matrix.
Yeah.
So that should help.
But you know, you don't have to truncate, because the point is that it's trivial to do it properly, because the Hadamard product of two variance matrices is positive definite. Okay, so here's the variance matrix that you want to localize. It has millions of small covariances. And here is a fully specified, correctly specified variance matrix with a Wendland, for example, compactly supported covariance structure, which has zeros for any 2 points that are more than 7 apart. You do the Hadamard product of the two, that is truncation, and the result is positive definite symmetry. So you don't have to just take this thing and zero all the very small values. You know, there's a well-defined operation that is not complicated to do, that gives you the...
So it is both positive definite and band limited.
Yep.
Okay.
Yeah. That
sounds nice, yeah.
Yeah, I mean, so they've been doing it recently in spatial statistics for exactly this reason. Right? When the observations come in, there's no point in working with tiny correlations if they're just going to slow you down. So what you do is you effectively compactify your covariance structure, and then you use sparse matrix algorithms to do the inference.
Sounds like a great idea.
Yeah.
Should have had that 10 years ago.
Any other questions?
Can I ask a question? Because we have the experts in the room, basically, so it would be a shame not to use the opportunity. So Michel Crucify and I have been building simple models for complex systems, in particular glacial cycles. And we build models which basically only capture the slow features of the process that we're trying to study. But naturally, the observations that we have to use are of much higher frequency. Okay? So we are faced with exactly the issue of the filtering problem that you described in some respects with gravity waves. Now, I spoke to Andrew Stewart about this at Warren, because he's worked in this area, and I asked him what he was doing in this situation, because I assumed that he would say that he was actually smoothing the measurements, in time, because that would have the effect of dampening the short-term variability. And he said that he actually thought a better approach was not to smooth the measurements, but to thin them. Right? Basically, to keep only 1 every 5 or 1 every 10. The idea being that
I think that's terrible. We are throwing out information.
Yeah, so this is the key thing, because obviously what he's doing when he's thinning is he's waiting for the variability of the process to become larger than the variability of the high frequency component of the observations. So he has 2 papers where he goes
do
to
thinning also when we use satellite data, because we expect them to have spatial correlations, errors on the smallest.
So thinning to the correlation of the local component of the error is very sensible. But I think Andrew would thin a lot more. He would thin all the way to remove all the fast components entirely.
Now, I would rather put in a constraint, so
No, I would project. In some way.
Yes.
You know, we haven't agreed yet on my second talk, so I might talk about this empirical model reduction business. Also, you are working with Michelle on
Yes.
projects.
Yeah, we've been working together for 4 years now on the project.
But I think thinning, if you do different kinds of thinning, so you are removing these, and you're removing these, and you're removing these, if they give the same results, then I think that approach is better than if you see that dependently of how you thin it, you get different results. So it should be possible to see if different ways of doing the thinning gives you the same kind of smooth curve.
Well, that's essentially an idea like bootstrapping or jackknifing or something like that. You could do that too.
So my preference is to try and achieve the best of both worlds by binning, right? Which is, of course, taking a window and creating one pseudo measurement from all the measurements in that window. But the reason that I do that in environmental science applications is because usually the measurements themselves are not Gaussian. But if you start binning, then you can use central limit theorem type ideas to motivate the use of a squared residual type loss function. Right?
And that's what we call super ops. I guess. Yes.
Sorry, is it very sensitive to the bin size?
The key thing is, as Neil says, is the bin size has to be large enough that the correlation length of the small aspects of the measurement process
Right. And also has to do with the size of the the model size, resolution, and
basically yes, we make the bins wide enough so that the components of correlation that exist that would exist otherwise in the loss function are basically zero.
I have one question. So you said that you combined the 3 wide with the ensemble method, and that you didn't want to go to full common filter formulation. Is it because you already have developed infrastructure for?
Yeah, and I would say one argument also is that we have the rank problem of ensemble common filter. That we keep the full rank of the static covariates and mix. That was at least our argument. And that we have, of course, we have the whole framework, and it was very easy to introduce. I think we can say when we have a high percentage of the ensemble constraint, it's another solution to the ensemble common filter. I guess it should be equivalent. So I think we combine.
Yes, I think there's a paper by which, or maybe somebody else, who shows that actually this is you can do it either in common filter or pretty wide.
Yeah. And it was so simple to do it in this way.
Yes.
Yeah.
Any other things you would like to bring in? If not, then we're thanking you again.